So today we will be switching gears. So far we were in Android. Right? We described different parts of the Android in terms of the application layer. In just like in the computer networks course, we start with the application layer, which and we talk about HTTP, SMTP, all the protocols. Then we go one layer below, and we talk about transport layer, which is TCP or UDP. Then IP layer, network layer, and then the MAC layer. Right? This is how we proceed. Even in the mobile, it's the same kind of stack. At one point at the top is the application layer, which is typically we are in this class using Android. Right? But after the world of the applications, all the applications, then you go one layer below, and that's where you have an operating system. Okay. This course is not about operating system only, right? And you will not have an assignment in the operating system. Okay, because it gets complex. But if one of you or some of you want to do some project in the Android operating system, you are free to choose it. Similarly, in the networks also. And whatever you want to do, I will try to guide you as much as possible. But this is typically a complex environment. It's not easy to code inside an operating system. So some concepts you already know, so you will just refresh, and I will then try to map it to the different world of mobile. So typically when we say an operating environment, right, it has all the software necessary to make your applications run. And that's the first thing from the application point of view. From the hardware point of view, they have a different requirement. But since we are computer science engineers, we'll look from the applications perspective. So you all know what software is, so I'm not going to talk about software, but OS is the glue between hardware and software. Right? That's where it all gets combined, and your application can execute on the hardware. Right? Just the hardware is not sufficient. Your application without the hardware is of no use. Right? So they have to work together, and the OS is the key. So let me give you an example of what happens in an operating system, typically on a mobile phone, not on the desktop. Right? So in desktop also some of the things are like this, but not everything. So if you break it from top down and you show it this way, your hardware is here, your operating system is the glue, and the software is here. So let me give you an example of radio. Right? So you have multiple of radios, NFC, Bluetooth, Wi-Fi, GSM, CDMA, everything. Right? All these radios, they are in the hardware, right? So you get some energy in the air, and that energy is captured by your antenna, and the antenna is connected to the real hardware chip, wireless chip, right? And this is this connection. So what happens is, if there is a signal which is coming in, the hardware will notify OS. So if you see this arrow, this is the notification going this way. It's not a busy loop in the OS which is continuously checking with the hardware. Whether you have received any message, whether there is anything on the radio, it's not doing this busy loop continuously. The hardware will detect it on its own. It has its own power, and it will do it on its own, and it will notify it. And we will see what this notification means, but it will then gets notified as a OS. OS, once it gets notification, it will find out the right software. It has lots of applications here, right? It will try to search which is the matching one. Can you remember where is this table mentioned in the operating system between the event that is happening and the matching application? I mentioned this, and I gave an example of Windows operating system. There is some structure where you have this mapping. What can be your guess? Task manager is when the applications are running and they are monitored. And this, what I'm asking is, you get an event or a notification and you break up one of the applications. System registry. And interrupts is also related. So today we will see both these concepts, right? More about this, in fact. But there is a registry inside every operating system where it has a matching. What if this event happens? What I should do? Right? In this verse, we say event and event handler. Right? So the software gets notified. The software is active. What it will do is, if it is interested. For example, if you get a phone call and if you see this is this number the call is coming from, and you are interested in picking up the phone call, you say accept. Right? Then that means you are interested, and then this thing goes more. Right? Otherwise, it just reject, right? And you cancel the call, and that's it. Right? In some of the cases, you cannot cancel, but in some cases where you can cancel, software then engages with the operating system, and it tells operating system, yes, I want to access this, then this will engage with the hardware, right? And you get the signals completely. And once the whole one data unit of it is there at the hardware will tell the OS that I have one full data unit, a logical unit, and this logical unit will get sent to the software. Right? So for example, in case of SMS, you can't really say I don't want to receive this SMS, it just comes. So that means the application will tell OS, give me the message, and then the hardware will get entire message. It has to get the header, the payload, the footer, then it has to make sure that the entire message is not corrupted, that it makes sense, and then it gives to the operating system. Operating system stores it within itself, and then it tells the software that such a message is there, do you want to read it? Right? And if the application is interested, then it gets a copy of the message. Right? So this is one paradigm, and this is applied everywhere in the operating system. Nowhere software is constantly checking with the operating system, is there anything for me? And nowhere OS is checking with the hardware continuously, is there anything for me? Right? This is all from bottom to up. Okay? And the reason this is this way is because it is energy efficient. This thing consumes less energy as compared to the case where everybody is polling the things. And if it's a busy polling, then you have to continuously check with the OS, and OS has to continuously check with the hardware, and nobody can sleep at that time. Okay? So this is how it is done. Right? And that is the same thing, and I will explain more about the interrupts and different kinds of interrupts in today's lecture. Have you heard about this term, interrupt, an interrupt handler? Yes. I don't need to go into much detail. So this is the example that I gave you. Right? This is in the text now. You receive the radio signal, right? The hardware notifies OS that the data has started arriving. And it's landing with me, and then the OS will engage with the sending software by working with the hardware, and it will get the complete message. It will tell the operating system will tell to retrieve the stored message, right? And then that in turn means interacting more with the hardware to get the entire thing. And then finally, the hardware, but at this end, if you see, the hardware and the software actually is not aware that there is an operating system. And that's another beauty of it. Hardware is also not aware of there is somebody which is operating system. It thinks the application is handling everything. And application thinks that it is making the calls to the hardware, right? And there is no such thing as OS, right? And ideally, in reality, this is not always the case. I'm saying here is the ideal thing. Right? Ideally, if OS is as much as transparent, that's the best thing. And if you start but thinking about OS as an application developer, what would OS do? That's where it's not a good operating system. Okay? So a good operating system is one which is fully transparent and it's not visible. Right? It's always in the backstage. Right? That's what we want finally. And everything that we design in the OS finally tries to be like this. So you take any operating system. You take Android, you take iOS, you take Mac OS, you take Linux, everything. Typically, they look like this. And this is the operating system. There's a big thing which we say system calls. Okay, let me There are system calls. There are lots of APIs like this which use a system call, and then this is your user application. Have you done any programming using system calls? Is there anybody? Yes. Which system call did you use? Anybody remember? Right, 4 system call. Right? Any other system call? Which one? Exact. Right. Any other system calls? These are the APIs. When you do file operations, right? What you're saying is open and so on. Right? These are mostly APIs that use system calls. So this is how it is done, and finally I will show you that really it's all the same. Right? Interrupts, system calls, hardware interrupts, software interrupts, everything is the same. We just give different names to all these things. So this is still an Apple device. It's an Apple. It's in a very old days. What was the year? So this is called Apple Newton. I don't remember. It's mid-90s. Right? They came up with this device at that time. So it's not like iPhone suddenly came into 2000, right? Or iOS suddenly came. They were working on it. They failed a lot of times. They came trying at it, and then finally they had a success. Okay, so very old days, there were handhelds. Does anybody know what were they called? PDAs. And this is where it all started. I think it was Portable Digital Assistant. Right? Personal digital assistant. So that's where it was there. Mostly it had ways of looking at your calendar and making notes and writing emails. Right? So this is how it all started. Right? But this was not really successful, and one of the things was that they did not have a good operating system. It's not like people did not want these kind of devices. People were interested in these devices. They wanted these devices to do a lot of things, but it's just that they did not have a good operating system at that time. They were even okay with taking a stylus and writing it down, as opposed to the touchscreen that we have today. Right? People were okay with stylus also, but what failed for them was not a good operating system. Right? And that's why they decided we should have something which is designed for this device, not something where we take Windows, delete some code of Windows, take it, put it on this device and make it work. It's not going to work like that. At that point, they decided, okay, now let's start from scratch, rewrite the operating system so that it's suited for this. Right? One of the issues with the Android, you see, is the battery consumption. It's a lot of people, what they do, they want to increase the battery life of their phone. If they have an Android phone, they root the phone and they clock it. There's some word called clocking. Right? At a lower value. That means your processor is running slower. By just virtue of making one change, your phone will last longer. Right? And a lot of people do it in the Android world. Right? It's because the operating system is clocking at certain rate and it is able to do a lot of things faster, and you see it's very responsive, but your battery is dying in the background. Okay, that's just one example. But you see, now you have to do something very dramatically different from the standard operating system and make it work longer, right? So even for the Apple Watch that they released, they haven't mentioned one very important thing so far. They haven't mentioned how long the battery will last with that watch. Right? They are still hiding it. Right? They mention everything, all the cool features, and they said, okay, this is this, and you can pay it, and you can do all sorts of things. It has a haptic sensor and everything. One thing they didn't mention, usually they do mention it, how long will the battery last? Right? And that's where the secret is. It should last longer, otherwise people will not use it. Okay? So now that brings us to the next point. Right? First of all, these devices have less memory. They have less storage space. Very slow processor as compared to the desktop, right? And it should be tailored for a handheld system, a very small system with a small screen. So what do you do with the operating system? Right? These are not only the issues. The big issue is also the power. It does not have a wall power. It lasts on a battery. So how do you make it efficient? If you all the time, it will drain the battery immediately. So another thing is it should not last longer also. There is another thing, the battery should be degrading gracefully. What does gracefully mean? What do you guess? Right. It should not be like this. Right? For some time it is going down. Right? This is not graceful degradation. As much as possible, you want to go from here till here in this fashion. Even if the life is the same, right? It should go like this because then the user otherwise gets confused. I'm calling and I'm making a phone call, the battery is 80%, suddenly it drops to 50%, right? Then it lasts for a long time, suddenly there is a big drop. It should not happen like that. So the OS should be designed so that there is this rate of degradation. So these are our specs. And then on top of that, it should support multi-programming like a desktop environment in a restricted manner and must save battery while coordinating access to many resources. Your laptop does not have NFC. Your laptop does not have GSM CDMA. Your laptop typically does not have touchscreen. Right? Your phone has all these things. And you still expect the phone to almost be same way responsive as a desktop. So this is, as you say now, if you are given this thing as an engineer, it's a very complex thing. And how do you do that? And that's where the engineering comes and it becomes complex. Questions on this? Did you understand the complexity? I'm not giving you any solution so far. I just gave you a structure of an operating system, typically what it looks like, and then I showed you all the complexities of this world as compared to the desktop or server. Right? You see, this is far more complex than a desktop operating system. Right? Even though it's small, it's more complex. So today what we'll do is we'll see different kind of ways that people have achieved this. And I will describe it at a very high level. I will not go at a very low level and tell you the APIs because that will then you will not get conceptual understanding of what's happening. Right? Another thing is it's not only everything that you do, it's also it has to be a good communication tool. And whenever you start using communication, your battery goes down very fast. Even on your laptop, if you want to make your battery last longer, the simplest thing to do is to switch off Wi-Fi. Right? That's the simplest way, and that will bring your battery and it will last longer. Okay? So on your phone, you typically can't do that. At least you cannot switch off the GSM. Right? You can switch off Wi-Fi, but not GSM. Right? And then you are also wanting nowadays all multimedia communication like YouTube, right? Music player, videos, phone calls, HD photographs, right? HD video clips, MP3s, right? So this is all you want without, and the battery should last at least for a day. Okay? How would you do that? What would you do in the typical operating system? Let me just pose you this question. I know that you don't have the full answer. You haven't seen what could be the answers, what could be the hints. But if you take the Windows, what will you cut down on Windows? Or if you are using Linux, what would you cut down on Linux to make it work for this environment? What do you think can be done?
Screen size of the Windows. The number of tables should be reduced.
So with the screen size is reduced. It's given to you.
The number of tables should be reduced.
Just so one thing with the screen size, you can do something. Because some of the Indian companies who have mobile phones, I will not name this because this is getting recorded, right? So I will not name the company, but they do some things. Do you know what they do? If you've seen those phones, yeah. So if you look at their phone, if you if you're not looking at the screen or looking as if you're not touching the screen, right, it will immediately switch it off. So you see that vendor and how quickly it switches off the screen as compared to the other phone, right? There's big difference, and this battery will last longer as compared to this, and then they will say your battery will last for 1 week. Okay, but the tricks that they use is this: immediately switch off the screen, and that saves you power. You're saying about the demons, right?
You could reduce the number
Yes. every Linux operating system or any operating system, when you start, it says how many processes can be there, how many daemons can be there, how many open sockets, and so on, all open files. You can hard limit these things to certain value so that you don't have to manage more things, and that will give you battery. Right? So you have already given me two things: screen, open resources. Anybody's got other idea to reduce battery? Brightness, yes. So it's related to this. So let me just write here brightness. You become very careful about the brightness of the screen. What could be other things?
The hardware all the time. The laptop will always stay ready if you have certain CD ROM or USB or switch on anything. From mobile, you have to communicate.
Yeah. So one more thing, and I will describe this in detail. It's related to what you're saying is and it's also related to resources. You don't load a lot of things at the beginning. So for example, if the user has switched off the Bluetooth and is not going to use Bluetooth, right? That means you don't load that driver at the very beginning itself. The desktop and the standard operating system might load it. It will not use the Bluetooth. Even if it's off, it will load the driver so that when the user switches it on, it's quickly responsive to Bluetooth messages. But your phone will take a long time to switch on the Bluetooth because it will load the module and everything very slowly. Right? So there is initial delay, but after that it will catch up.
Does it reducing the number of resources come into this?
It's the same thing, right? It's more. I gave one more example of it, and so that's another example of it. Any other thoughts?
Peripheral modules. Like scanner and all these modules right here.
So what will you do on the phone?
You don't need so much peripherals for phone.
Mm-hmm.
Like scanner and all such modules are not needed for phone.
Mm-hmm.
Like Ethernet ports.
Right. Right. So some things if you don't have on the phone, you just don't compile it and load it in the operating system itself. Right. And we will see an extension of this. Other things?
Mobile data, network data, like packet data,
Right. So what will you do for the packet data?
it drains the battery faster.
Okay. So this is what they typically do is, one thing is if you have very small data packets, you can send every packet immediately, or you can wait till you get enough data to fill in one packet. Right. So for example, YouTube. Right? YouTube is actually bombarding you with a lot of data all the time. Right? That means their packets are always full. But Facebook notifications, if you look at it, and these are short ones. Right? What can be done is you don't take every notification and put it on the phone and display it immediately. You wait till everything gets combined for Facebook communication, right? And then one packet gets full, and then you actually send it or receive it. That way, your latency increases, but then your battery life is better because sending 5 different packets, small packets, consumes more energy as compared to sending one big packet. Okay. So data communication. So let me give you this. I will skip for now, real-time system. I will come back to this. So this is typically any operating system looks like. We typically categorize any operating system into these three, one of these. We see either it's a monolithic kernel, you all know kernel. So, or it's a microkernel or it's a hybrid kernel. And this is how we classify it. Monolithic kernel is something which has everything combined inside the kernel. So kernel is really big. It has lots of drivers and components and servers and everything together. Two examples well known is Android and Linux. Of course, Linux is the first one, and Android, since it's also Linux, right? It's falling under the monolithic kernel. Then there is another kernel which we say microkernel, and this was invented at CNU. And what it does is it provides a very small set of system functions, minimum, and we will see what the system functions are. But these are minimum possible, and much of the remaining functionality, of course, you don't have everything in the kernel, so where should it lie? It lies outside the kernel and is provided by something which we say server applications. It's not the standard applications that you write as a developer, but it's a server application. And one example of this is the Symbian OS. Right, so this is microkernel, this is the monolithic kernel, and this was really the first operating system for handheld devices. Because they thought at that time that this would be the best application for a handheld device. Okay? And then there is another kernel which is hybrid, which is in between these two. And it's not fully blown monolithic kernel, but it is not also the micro part of it. It's somewhere in between. And that's what we say hybrid kernel. Right? So some things are implemented inside the kernel as opposed to an application server to make it faster. And the example of this is macOS from Apple and iOS. Okay? So if you want to look at now 3 operating systems, right? This is where the iOS and macOS, this is the Linux world, Linux and Android, and this is the Symbian OS, right? And this is how it stands. Or at least if you're looking at the mobile operating systems, this one, and this one. Right? So these 3 are in 3 different spaces. And by nature, by design, they will have all the features, advantages and disadvantages both of this concept, hybrid concept. Right? And this will have problems and advantages of microkernels. And Android will always suffer from some things, which is the problem of having a monolithic kernel. Have you seen any one of these kernels? Have you studied these operating system kernels? Which one did you see? All 3? Okay. So you know in some level of detail, but to give you a little bit more detail, the monolithic kernel will look like this. There is one kernel base, one usual software, hardware, and it looks like this. And the microkernel is kernel, and there are some servers which are continuously running on the device, right, which are not in the kernel space. Right? These are what we say kernel space. And we'll see what kernel space is. And these are servers, so user software will first talk to the server, and server will talk to the kernel, and kernel will talk to the hardware. Okay, now can you tell me advantages and disadvantages of these 2 approaches? I'm looking at monolithic and microkernel. And one advantage of this, and disadvantage of this, and one advantage of this, and one disadvantage. You can take 2 minutes. From what?
The microkernel will load very fast at the beginning.
You take a minute, write it down and then tell me. Because you should give me advantage, disadvantage, here advantage, disadvantage. You can talk to your neighbors if you want, that's okay. So what is an advantage of this? It's fast. Fast in what sense? Why does it make it? What?
Loading.
Yes. So initial boot time.
This one is
Very good. So what is an advantage of this? Where will it be fast? More responsive because right. This is one level of indirection here, right? And this it directly lands inside kernel. So at the time of maximum time when it is up and running, after up and then continuously running, this is more responsive as compared to. So what is an advantage of this? Loading. Right? Being it's a microkernel, it's a small kernel, so at the boot time when you load for the first time, it immediately boots up. Right? And it's faster. Okay, now disadvantage of this, I think you can just make advantage of this as disadvantage of this and so on. Right? It will take time to boot. Right? Another thing is also there is a modification inside the kernel. You want to change the kernel. Right? The problem with Linux is if you want to recompile the kernel, it takes a long time. Right? So that's why it becomes cumbersome to modify Linux kernel very fast. You have to just recompile everything, big thing. Right? So, but this, the advantage of this okay, let's talk disadvantage.
Yes.
Less responsive?
Less secure.
No. So we are not compromising on security in either case.
That is outside the kernel space.
Let it be. No. We can't change that level. We can't say, okay, we will give you less secure, less private, right, thing, and but it's fast. That cannot be done. Operating system has to be secure. Right? It's not yes or no there.
The level of security in that kernel space and outside that server in the user space is same.
These two are equally secure. Right? They have designed it, and maybe we will discuss it how it is done. But security-wise, at the end slide, I have one slide which will talk about this. These are equally secure. Just because you made some things outside doesn't mean it is insecure, right? As you can see, there is always something which goes to the kernel. Right? So it's not less secure; it's the same secure. Okay. So if you look at now the microkernel OS. In fact, this is the microkernel, and within it we see something called a nanokernel. And it just makes it very small. Then the microkernel, then these servers which are sitting outside, and then the user mode application. This is how the system will look like when it starts up. Okay. All the things that are there in the nanokernel are things which are simple. Like scheduling, synchronization operation, interrupt handling, mutex. What is mutex? Semaphores, right? And the standard general semaphores. This is for mutual exclusion. Right? So these are the things that operating system has to do. Right? It has to do these things, and that's why they become part of the nanokernel. And that is required. Without it, there is no operating system. Right? And most of these functions can be preempted. Okay, what is preemption? OS can boot it out and do something else and then bring it back. Okay? This is a very important word. This is what I'm saying is most of the things are preempted. Okay, and we will see this and then we will do a comparison. Operations are primitive and fast. So for example, you don't do something like dynamic memory allocation, which takes a long time. You have to search for the memory, get a consecutive memory block, find out the pointer in the pointer, give it to the application. All that takes time. So you don't do this. You do just very simple things. Semaphore is a simple operation. Synchronization, scheduling, these are all necessary and simple operations. So this is part of nanokernel. And then you have the kernel, the other kernel, outside kernel. So this is also privileged. This is privileged. This is also privileged. And it combines these primitive operations of the nanokernel to implement complex tasks. And what are these complex tasks? These are something which is you have defined object, you create objects, and you pass on the objects, threads. You have user mode threads, not kernel threads, but user mode threads. Then you do process scheduling, context switching, changing between one process to another process, and you all know the scheduling algorithms. So I will not talk about different scheduling algorithms. Dynamic memory here. And then dynamic loading of libraries. At runtime, you you can load libraries as compared to static time. All these are part of the duties or chores of the operating systems, and it will do it here inside this part, but not inside this one. Now here it is fully preemptible, and interrupts can cause this layer to reschedule any part of its execution, even in the middle of context switching. So context switching requires you to preempt something, and while you are doing that, you can preempt yourself. It's a recursive thing. Okay, now can you tell me why this is an exercise? It's a thought question. Why this is saying most of the things are preemptive, and here I am saying everything is preemptive. What is the difference? Why cannot I have that? So first of all, having preemption or having a capability of preempting something, is it good or bad? Why is it good?
Because the more prioritized process can be.
Yes, it's good that if you have capability to throw somebody out, right? Because then you can do more things. If somebody is occupying the space and not leaving it, right? It's not under the control. So operating system, as much as possible, wants all these capabilities. But now what I'm saying is, so this is not really good, right? Most of the things are preemptive. This is what we want. But why is it most of the things are preemptive? Not everything is preemptive. Can you give me a reason when I'm saying why most of the things are preemptive? For example?
For example, if you are running your battery and you get an interrupt, so you cannot ignore that. It's not a system issue, but something.
So you're talking about priorities. Okay, so there is one thing about priority. But priority is different, as in if you have something that's got more or higher priority, you don't want to interrupt it. Right? What could be other reason that you don't want to preempt it? So this is about priority. If you throw it out and do something, you just violated the priority. Okay? But what could be other reason which is more serious than priority?
Maybe you don't ever want some simple background processes to be preempted. You always want them to be running forever.
Right. So answer is there in the slide actually. You are also, it's about the priority, right? But what I'm saying is I'm not talking about priority. I'm talking about very important things. If I allow that thing to happen, operating system might crash. Okay. And the answer is there. We have done it in the operating system course. Yes? Yes? Semaphore, very good. Right? So semaphores, what does semaphore mean? Synchronization. If two threads of control are operating on the same variable, right, you don't want it to go inside a race condition where the things will determine what will be the final value depending on who came first. So you provide semaphores, and what semaphores say or mutex say is there is some operation which you cannot predict. Right? You lock it. Locking and unlocking, and in between things it's not predictable. If you allow it, your operating system might crash. Because then it's very like simple things like clock value or who is operating on which file, whether your library is like getting loaded or not. All these things depend on these. And if two processes operate on it, it will corrupt the system and it will finally crash upon operating system. Right? So some things you don't want to be preemptive. And because of that, some of the things inside nano kernel are not preemptive. You don't allow it to be preemptive. But in this kernel, you take out all these other operations which are preemptive. So you see, we are looking at this as a very mathematical thing. Even though I don't know anything about C or pointers or anything, right? I can still understand these things. And these are things which are common. If you come up with a new operating system also, no matter how good C programmer you are, and you are the best hacker in the world, but if you make mistakes here, your operating system will still crash. Right? No matter how best programmer you are.
So, does the kernel also have some of the, what is the replacement?
So we are talking about this level of kernel, a nano kernel, micro kernel, and so on. You can of course create the entire kernel like a monolithic kernel. I gave you an example about monolithic kernel here, right? And it will all sit here. And then most of these operations then are not preempted. But if you come up with some division like this, where some things, right, you keep outside the big kernel, the small kernel, right? Then you start with only small kernel, and you put it with that kernel. And as more things are wanted, you populate the outside kernel, like this. Let me go one slide before. Like this. So this is something which you have, which is most of the things are preemptible. Here, everything is preemptible, and of course, as you go outside, everything is certainly preemptible. Right? And you want to minimize the things into one place where these things are not preemptible. But if you make a very big kernel like this, and almost everything is not preemptible, right? You end up in a kernel which is big and non-preemptible.
Can you repeat the reason why Semaphore process needs to be preemptible?
So this is, you might have to look at this book of operating system and look at semaphores. But overall, it's something like this. There is a lock operation, and then you unlock.
So my question is exactly this. Once if a process has done this, it has acquired the lock.
Yes.
Even now, if the OS preempts this process and comes with another process in place of this, the another process will not be able to.
So I'm not talking in this in terms of application programs, locking and unlocking things. Right? Application program will typically use, what are the operations on semaphores? Wait and
Signal.
right? And there are binary semaphores and so on, right? Let's not go into detail. Let's take a simple example of semaphore. You have a wait operation and a signal operation. So this is what the API for the application program. Right? This gets translated at some level in assembly language code, which is doing this lock unlock business. Right? And between, when I say lock and unlock, that means do not preempt me while doing these things. And this is where if we do something with this variable. Right, critical section, what we say. So at this point, you don't want to get preempted, because if you get preempted here, it might have an incorrect value. Okay. Now application will call this. Kernel will have these things inside in its assembly language, and you don't want these things to get preempted, and that's why you put it in the nano. Other doubts about this? So to take away from this is, if you build an operating system like this, which has a very small component, then it can have most of the things preemptible, certain things will not be preemptible. Then you have another layer where almost everything is preemptible, and you go from there. Right? And then there are some servers which are even sitting outside the kernel, and they talk to the kernel and they get their things done. Right? And both things, and neither of these two things are insecure. Now, I will talk next, last slide. Okay. So inside every kernel, there are some things which are active and some things which are passive. Now we take any example of any kernel. I'm not just saying about one kernel or the other kernel. Right? Every kernel will come with passive and active components. So these are the active components which are continuously executing. To give you directly an example, a global memory maintained by the kernel for two processes, or context switching, the things that is continuously switching context between processes, that is always active. And the one which loads module, it is always active. One which is looking at what is your CPU utilization, memory utilization, when you do the top, all these things are continuously active. They cannot sleep. And they will wake up after some time, that's constant amount of time. They will do all these housekeeping operations. They will go back to sleep and they will come back again. Right? And these are the components which you have to have. And so if you want to have a better operating system, energy efficient operating system, what should you do? What should be your criteria for active components?
Active components should sleep for
much longer time, and there should be less number of active components. Right? First thing is you try to see you have less number of active components, and on top of that you see they should be able to sleep more amount of time. Right? So you again look at your operating system and see how many active components do I have, and then you compare it with another operating system and see how much does the other operating system has got. If you have got more, then your battery will die quickly. Right? There is nothing more about that. It's just simple science. So you design operating system, cut down the things which are doing this bookkeeping and housekeeping things continuously, and that will give you better battery life. But you cannot have zero active components, right? Zero active components means your operating system is dead. One thing that it should have, what is the one thing that it should be there without it? Time you need clock. And so you have to stand for, okay, this is this time right now, and then you go back to sleep and wake after 10 seconds. So clock has to run continuously. Okay, and then you have other things. Then the passive components. Yes. So every component that I said, even so these are the components you can see are doing busy loop. Right? And then you don't want to wake them up at a very high rate. Right? If you can wake up after, let's say, every 2 seconds, it is better than waking up after every 1 second. Right? But now it depends on what kinds of things you want to achieve. If the things demand that you should wake after every 1 second, then you have to wait. For example, if you can receive messages at a very high rate, for example, something like an optical connection, where you can receive very high rate, you can't sleep more. Right? I'm just giving an example. This is not real example, hypothetical example.
I'm not understanding how does the active component sleep and wake up? What does this term actually mean? The active component is always active.
No. So inside every processor, right, you have things going on and running continuously, right? And then the CPU actually is looking for the time where it can sleep, take a nap. Right? It is always looking for taking nap, right? And the more it sleeps, so you may not believe, but this whole CPU is actually sleeping in between, and you may not notice it because those sleeps are very small, but they actually go down. Or what they do is they become slow, they become sluggish, they reduce the clock rate. That's also similar. It's not full sleeping, but it's reducing the clock. And as much as possible, you want these things. So, for example, if you give a process a time slice of 10 seconds, then the thing that is looking at scheduling does not have to wait for 10 seconds. Because that process will continue running. Right? So the process, the active component which is doing the scheduling, can sleep for some time in that time. So if I give you the CPU and say you execute as a process P1, this thing which is giving the scheduling can sleep for 10 seconds. So there is sleep available for every process. It's not like you cannot sleep at all. So advantages are like this. You can go to another example that I've given for minimizing the active components. I've already given you one example. Let's another example. Now looking at this, what are the passive components? Passive components are some things which are not continuously running. One example is if you have infrared sensor, like if you have a remote, and it has an infrared transmitter and receiver. You talk, and if your phone also has got that one, and you may not typically use it all the time. Only when you really want to operate it, you will use it, and then you will load it. So that's the passive component, which is not continuously active. It's only on demand. You make it active, you use it, and then you might unload it also. Right? So device driver. For example, the USB that you connect on your laptop, that driver is not loaded a lot of times. When you connect it, it gets loaded, and then you stop it and then go. Right? So that's the passive component. So you have seen the software interrupts, and another word for software interrupts is system call. Right? So it's basically an interrupt. Everything that happens, if you remember the first image that I showed you about the hardware, operating system, and the software, and then this is event and engage and notification. Those things that were events, these are interrupts. Right? So everybody interrupts somebody else at the high level and they give something. Okay. So this is also an interrupt. So it is, if an application want to wake up something inside the kernel, they will use an interrupt. Okay, because operating system is working on its own and the app says, okay, I need some service. So it will interrupt that guy, and that is through system calls. And so this is how you interrupt the operating system. So operating system does not have to busy wait on the application and see who wants the service. So these are implemented as software interrupts, and similarly hardware also sends interrupts, and those are the different interrupts. So one important thing, and I will talk about the security question after that, is whenever you have interrupts, you go into, we say, privileged mode, or as I written here, is kernel space. So whenever an interrupt occurs, software or hardware, the OS, the entire thing goes into a privileged mode. In privileged mode, you can take some actions which otherwise are prohibited. For example, you can look at your hard disk, you can look at sectors, cylinders, you can look at your USB disk, what file system it is, you can go to the boot sector 0 and look at there what it is written, you can rewrite. Right? Some of the things which are otherwise not allowed. So for example, your screen also. The screen is typically not, an application cannot get full access to the screen, because if it excites different voltages, it might permanently damage your screen. And if you get some operating system which gives high voltages continuously to the screen, it might damage it. Right? So there are some operations which are privileged, and you can do it only inside the kernel. Okay. Now one question that was asked is, how is the other thing where I have servers? Is it less secure or more secure or equally secure? I said it is equally secure. Let me show you that slide. This one. Right. So how come this is equally secure as this one? What do you think? Because inside the kernel you are in the privileged. Right. Now, is this less secure? It is equally secure, as I am saying. So how is it equally secure? This is again a question. What must have the designer do? Yes. Right. So the way you looked at this is you take all the operations which are privileged inside the kernel and you squeeze it inside this part, this block. Whatever things which do not fully need privileged access, which do not need privileged access, you take them out and you run it as a server outside. Right? So for example, if I want to access a cylinder on your hard disk or a sector on your hard disk, right? There is a lot of operation in just sending commands and buffering the data. All this buffering does not need to be privileged. Only the final thing when you write it, that is a privileged operation. So what you can do is all that buffering and everything you factor it out and you put it inside a server. So the app will directly talk to this server. It will give all the data to the server. Server will collect all the data, and when everything is ready, then it will just create one interrupt to the kernel and tell it to write it on the hard disk. And it will do it in one operation. Right? Now you can see, typically what we do here is, right, app is constantly in touch with the kernel here and sending this data. Right? And then unnecessarily you stay in the privileged mode for a long time. Right? But in here you stay it for a moment only when you finally write it to the disk. Right? So that way it is equally secure. Right? So this was the question. So you design the servers accordingly so that it does not need privileged access. Right? So that way this is equally secure. Most systems do not allow application level code to perform kernel mode actions or privileged mode actions. They have to use the system calls. Can you tell me how is application level code not able to execute this code. Privileged code. I think that's where we'll stop. So my question is, now this is a general knowledge question. Right? I'm not going to teach you much about this right now after this point. We'll summarize this. My question to you is, how is the app not able to execute any privileged mode operation? If I take the privileged, so let's say this block is a privileged mode operation. It is block. Right? Why not I put it inside my assembly language code as a developer and execute it?
There are two spaces, basically kernel space and user space. So the application can only concentrate in a user space, and the kernel has the privilege to use the kernel space for its kernel space.
Right. So why cannot I go to kernel space? I say I want to go to kernel space. I go inside kernel space. So I enable that bit.
That is possible only through system calls.
Okay.
So kernel can reject your
Right. Right. So that's where it stops finally. The bug stops there. Right. What happens is you have to enable one bit, which will put the processor CPU inside this privileged mode. And the only way you can do it is using a system call. Right? You cannot call this action otherwise directly. If you call it directly, what will happen? If you call it, it's a simple instruction, right? If the kernel can call it, I can also call it as an app developer. What will happen if I call that instruction? That assembly language instruction, which sets the bit.
you can damage the hardware.
No, but you cannot do that. Right, so the question is that what you're saying is there is one instruction, let's say the super instruction. This is some super instruction that is going to set the bit and put the processor inside the kernel mode. Right? I just copy paste this instruction and put it inside my application and call it. You can give it a try. Just find out for your processor what is that instruction which sets that bit. Copy it, put it in the assembly language code, execute it, and see what happens. Now theoretically, this is theory class. So theoretically, what should happen or what will happen? So how do I not allow? How do I tell app, okay, don't do that? So not allow means he's not going to listen to me, right? He wants to do it. Not allow means what?
Super user privileges only the application should be allowed.
So there is a chicken egg question right here now. Right. What I'm saying is, see, this is, I call this instruction. So what you are saying is, there is something, some instructions, which if I call in the user mode, I get an error saying this is not allowed. Right? But I am calling that instructions which will put me inside that space. That thing will come if I am calling something which is like I'm already in that space or not. What do I do that?
So I think kernel knows from where this instruction is. Like is firing himself and
very close. What happens is you can't call this thing cannot be called from anywhere. Right? There is one part of your hard disk which is read only. Which is once you switch on the machine, the OS does some magic and makes one part of your hard disk read only. And this instruction can be sourced only from that point. Right? So your app will never be on that memory space. It will always be at a different space. So that's why your bootloader and the OS, that sequence is important. Because it starts loading things and it makes some things read only. So it will take the code and put it inside memory here and it says read only. Right? And only I can call it. Only this thing will call it. This piece of code in the hard disk, one part of the hard disk, it will only call it, nobody else can call it. Your code will always sit somewhere here. Right? And OS says, if you call it, I will not allow it. Right? So you better make a system call which will take me to that interrupt handler, which is sitting in that memory space, and I will let it call. Right? So if you want to enter this mode, you do a system call, and you enter one privileged space inside your hard disk, which is read only, and only that can call this instruction, and the OS will allow it. Right? So no other part of your hard disk can put these instructions and make this call. Okay, so that's where you have to have OS to make it secure. Right? Right? And if you root your phone, you lose all these securities, and then your operating system might crash. That's why they said, okay, don't root your phone unless you know what you're doing, because then anybody can call this, and it can get root access. Okay, so this is a general knowledge. This is not something I will ask you in the exam, right? But this is how the operating system protects you and protects itself also. Okay. So what we learned today, let me just go back very quickly, is we look at the challenges of, we looked at how typically in any mobile operating system the way things work. Where is the hardware, where is the OS, where is the software, and how they talk to each other. Then we looked at example of text message, and I told you all the complexities of a mobile operating system. Right? What are things which will differentiate itself from a standard operating system, right? And power is one of the most important concerns. How to save as much energy as possible, right? And to handle this, we looked at 3 different kernels, way of designing kernels, and we saw advantages, disadvantages of this, and then in the market, which is using which type of kernel. Right? Android is using what, Symbian is using what, and Hybrid is using what. Right? And then we saw for a microkernel architecture, what are its components, and what things can be preemptible, what things are not preemptible, and what is the reason behind this. We looked at different active level components, and we saw we have to minimize these number of components, and also we have to give them more chance to go back to sleep, and then that will increase the power efficiency. But there are some components which are passive and which gets loaded only when it is required. Then that level of engagement and notification, that is it's in call, system call, or interrupt, or software interrupts, hardware interrupts, right? Different names, but finally it's the same thing. And as you see, this does not need busy waiting, and that's why this is more energy efficient, and it will give you more power. And then we looked at an example of how security is ensured with the system call. The system call means you will enter privilege mode and you do certain operations. But I showed you an example and told you about how to ensure that an application developer, programmer will not be able to go inside a privilege mode by itself, because it is not allowed to call that instruction. Okay. So there is a quiz. Just take 5 minutes. There are only 2 questions. Right? It's CSC 535 monsoon. CSC 535 monsoon 2014. So go inside this classroom. There is one quiz. I think there are 3 questions. There are 3 questions.